All right, so as I try to see whether or not we can actually take care of the... What is up with the glare today? This is like a totally new glare problem. Okay, hopefully this is going to work out okay. So, what we're going to do today is we're going to keep on talking about these Riemann sums that we've had. And what we can do with them and just say a few things about them. I'm sorry, I got to secure this thing. It's going to drive me nuts. I really need better attachments for this stuff on my wall. So we're going to say just a few things about what you can do with Riemann sums. And then eventually what we want to get into is the fundamental theorem of calculus, which I've already sort of previewed for you a couple of times. But before then, we just want to say a few more things about Riemann sums and whatnot. So first of all, some notation. The notation that I want to introduce here is known as the definite integral. And the definite integral is written in the following way. We write this big elongated S, we put a and b here, then we put some function f of x, and then we put dx, which tells us the variable that we are integrating. So there are two ways of defining this. This is equal to the limit as n goes to infinity of the sum from I equals 1 up to n, f of xi star b minus a over n. If this exists independent of choices. So that is our first big thing. Does this exist independently of choices? Now, this is the definition of the definite integral in terms of Riemann sums, and for this reason, it is also sometimes known as the Riemann integral. I mentioned last time, but I'll just remind you that there are other ways of defining integrals that are rigorous and technically correct. Okay, so Riemann came up, he was the first one to come up with a really rigorous definition of the integral that proves that the integral is well defined. However, his definition does have some technical limitations that won't really affect us, but that do concern mathematicians in general. And for that reason, other people, Lebesgue and Daniel, came up with other ways of defining the integral that are a little bit more technically complicated, but that have some nice properties, at least nice properties for mathematicians. I'm sorry, I'm adjusting my video again. Maybe that's, okay, there we go. That makes it a little easier for you to see me, maybe. So, now I want to say this is the technical definition, but I also want to give you a little bit of an intuitive definition of what this is equal to. So the intuitive definition is it is the area above the x-axis and below y equals f of x minus the area below the x-axis and above y equals f of x. Now, we looked at this last time, okay, and we saw why this quantity is of interest. Because right off the bat, you look at this thing and you think, why do I want to do this thing where I add certain areas and subtract others? Well, yeah, we saw last time why this is actually a quantity of interest. And the reason is because if your function describes a rate of change, then this difference in areas, where you add the ones above the axis, you subtract the ones below, this should actually describe the total change if the rate of change is described by f of x. Of course, in a lot of cases, when it's a rate of change, we might use a different variable or whatever, but variable name doesn't really matter. So it's the same either way. So yes, the definite integral can intuitively be defined this way. And in fact, this is sort of the way that people defined it originally. The problem is you have to make sure that these areas can be defined precisely. And that's what Riemann's definition does for us. It gives us a precise definition. However, the problem with Riemann's approach is that it is a royal pain. Nobody wants to actually compute limits of Riemann sums. We're going to do it in a minute here. We're going to see what happens, but it's not easy. So let's, on that note, talk about some approaches to doing Riemann sums. Special Riemann sums. We will return to these definite integrals in a moment. See, the problem with the Riemann sum is that there's an infinite number of choices. We can choose for each n and for each xi within that Riemann sum at level n, we can choose a point in the ith interval. So the problem is, how do we choose the xi stars? Well, a couple of fairly obvious choices sort of present themselves. At least they're obvious in the sense that they're relatively simple to write down. One option would be, if I have this interval from A up to B and I cut it up into some pieces, I'm just going to cut it into 4 pieces here. One sort of obvious option would be to do the left endpoints, which I will abbreviate as LE. We could also do the right endpoints, which I will call RE. Finally, we could do the midpoints of the intervals, which I don't really have a good abbreviation for, so we're just going to call them midpoints. How do you get the left endpoints? Well, the answer is, in this case, you would take xi star to be equal to A plus I minus 1 times delta x. Because that would mean that x1 sits here at A, x2 gets bumped over by delta x to the next left endpoint, x3 gets bumped over to the third left endpoint, and so on, okay? So this is what you do. And like I said, one of the reasons for choosing left endpoints is simply because it's relatively simple to write down the left endpoints. What about right endpoints? Well, these are almost as simple. For the right endpoints, xi star is going to equal A plus I times delta x. So this would mean, x1 is A plus delta x, which is actually the right-hand endpoint of this first interval. And it can, I'm not going to bother writing this out. I think you can probably see the pattern that's going to happen here. Each time we increase I by 1, we bump ourselves over by delta x. Now, the thing is, these are only 2 possible choices. And really, in order to deal with the Riemann sums, we need to show that these limits exist independently of our choices. And that's where things can get a little bit tricky. It's also kind of where things get messed up in certain technical examples. So it's not simply that it's hard. It's not hard because it's just hard in itself. It's hard because actually often this is where problems arise, is in making sure that the limit exists independently of choices. You can often show that for some choice, the limit will exist. The problem is to show that for all possible choices, the limit exists and it's the same number. Oh, and what about midpoints? I didn't write down the midpoints yet. Here's the way that you choose the midpoints. It's a little more complicated, still not too bad. So for midpoints, and you might want to actually, in fact, take a minute, see if you can figure out how would you write down the midpoint of the ith interval. It's not really that difficult. And now that we see the left endpoints and the right endpoints. Well, the answer, and I hope that you spent a minute actually thinking about this, but the answer is you just average the left endpoint and the right endpoint. So that would mean that I take a plus I minus 1 delta x plus a plus I delta x, and I divide that sum by 2. This actually simplifies into a plus, how do I want to write this? Because it simplifies in a weird sort of way. Let's say it is a plus, yeah, this is a good way of writing it, I minus 1 half delta x. And you could actually figure this out without averaging too. You could just sort of reason your way through it, because the first midpoint is going to be a plus 1 half delta x. The second one is going to be that plus an additional delta x. So our first x1 is going to have to be a plus 1 half delta x. Then x2 is a plus 3 halves delta x, and so on for our midpoint formula. And it's not too difficult to see that this is the pattern that you're following here. Okay, so you can figure out this pattern without doing the averages, or you can just do the averages. Either way, you get the same answer. So there's the midpoints. Now, for some purposes, it might be worth actually writing down some specific Riemann sums. For instance, we could say, let's write down the Riemann sum for the integral from 0 up to 2 of x cubed dx for n equals 4, and let's do left endpoints and then right endpoints. I will leave the midpoints for you. I mean, like, these writing down the Riemann sum problems, what it comes down to is they're usually just kind of long and tedious, but as we will see, there's not any like very difficult part of them. It's just that they're long. So it's easy to sort of lose focus and make a mistake, but you know, there's not anything really tricky going on here. Because all we're going to have to do is we're going to write down the left endpoints. So I will make a list of the left endpoints. If I break up 0 to 2 into 4 pieces, then those pieces are going to happen at 1 half, at 1, and at 3 halves. And in fact, you can notice here, delta x is going to be equal to 2 over 4, which is 1 half. So the width of each of these is going to be at 1 half. The left endpoints are going to be 0, 1 half, 1, and 3 halves. So the Riemann sum for n equals 4 and left endpoints is going to be 0 cubed times 1 half plus 1 half cubed plus times 1 half plus 1 cubed times 1 half plus 3 halves cubed times 1 half. This is going to be equal to 1 half times 1/8 plus 1 plus 27 over 8. That's going to become, why am I confused by this? 1/8, so that's 28 over 8 plus 8 over 8. 28 over 8 plus 8 over 8 is 36 over 8 times 1 half. So this becomes 36 over 16, which is 9 over 4. Okay, so like I said, the thing about this problem, it's not like it's a hard problem in some sense, as long as you know what the definition of the Riemann sum is. It's really just that it is a long problem. And if n is even bigger, it's a really long problem. So here's the left endpoints. Now, let's take a quick look at the right endpoints. In fact, take a minute yourselves, try to work out what happens with the right endpoints and see what you get. And then we'll work through it together. So the right endpoints are almost the same, except when I make my list, we start with 1/2, then we have 1, then 3/2, and then 2. And so we're going to have, for our sum, we have 1/2 cubed times 1/2 plus 1 cubed times 1/2 plus 3/2 cubed times 1/2 plus 2 cubed times 1/2. This is going to become 1/2 times 1/8 plus 1 plus 27/8 plus 8. And what is this going to come out to be? I wish that I had left the other thing up now, but I really didn't have any space. Well, yeah, so this is going to become 1/2 times 36/8 plus 8. That's going to be 36/16 plus 4, which is, I'm sorry, I've run out of space. This is going to be equal to 9/4 plus 4. And so that is going to be 16 plus 9 is 25/4. Okay, so like I said, long problems, not really particularly tricky problems. If you wanted to do the midpoints, you could do that as well. But what are the midpoints? Well, the midpoints here are going to be at 1/4, and then at 3/4, and then at 7/4, and then at I'm sorry, 5/4, and then at 7/4. I'm like, how did I get up to 9/4? That doesn't make any sense. It's because I managed to skip a number. And then you just plug them into the same sum. And the thing is, with the midpoints, you get slightly messier fractions, right? But you're not doing anything fundamentally new. When we write down the thing for the midpoint, we still have, it's just going to be 1/2 times 1/4 cubed plus 1/2 times 3/4 cubed plus 1/2 times 5/4 cubed plus 1/2 times 7/4 cubed. Okay, you get the picture here, right? So it's not like there's anything new going on. It's just you got to add all these things up. And frankly, this is where a computer becomes a really good option. Like, computers are good at doing arithmetic for you very quickly, where you don't have to do any thinking about it. So I'm not usually a big fan of using calculators, but in this case, I am pro calculator or pro using a computer, because nobody wants to do this by hand, and it doesn't give you any enlightenment to do this by hand. Just throw it into a computer if you really need to do this. Now, by the way, why would you want to do this? Well, one reason you want to do this is because it gives you an estimate for a definite integral. So notice we can approximate the integral from a up to b of f of x dx using a finite Riemann sum. In other words, we may not necessarily be able to calculate this definite integral exactly, but maybe we can get an approximate number by just finding one of the Riemann sums with a very large number of rectangles. And this is something that computers are very good at. So engineers, for example, or other people who don't always need exact answers, if you only need an approximation, you can have your computer just do some finite Riemann sum, and you hope for the best that this Riemann sum comes out to be pretty close to your answer. Now, the problem is that depending upon how messy f is, your answer here could be completely off. So people who deal with computer science and with the field of mathematics known as numerical analysis, they spend a lot of time thinking about things like, how do we know the possible error in our estimate here? Like, you do a finite Riemann sum, how far off could you be from the real answer? And then, there are formulas that you can come up with that give you a bound on the error, and then you can do things like say, okay, let's tell our computer to keep on increasing the number of rectangles until our error is below a certain bound. Like, maybe I just need my answer to be within 1/10 of the correct answer. And that's good enough, because maybe, for my purposes, I don't need a very exact answer. I just need something pretty approximate. Maybe somebody else comes along and says, no, for my purposes, I need to be within 1/10,000th. Again, you can do that. And this is a whole field of mathematics dealing with how do you get these estimates and whatnot. For our purposes, I just wanted to illustrate how you write down these Riemann sums and things like that. Now, here is the real question. How do we know what the Riemann sums converge to, and how do we know that they converge to the same thing? Well, I want to show you an example that we're going to think through. And as we think through the example, it's going to kind of illustrate for us how to generalize this idea to other cases, okay? So the example I want to do is, let's actually calculate the integral from 0 up to 1 of x squared dx. We are going to actually do the limits of the Riemann sums, and we are going to show that all of the limits of the Riemann sums come out to the same thing. It's going to be very, very annoying. And we're only going to do this with one example because it's going to be, as I say, annoying. But it will illustrate how you do this, and it will also illustrate for you why we want to come up with a better way of doing this, which is the fundamental theorem of calculus. Here is my observation that I'm going to make to start with. On the interval from 0 up to 1, x squared is increasing. Now, that may seem like a trivial observation. It's not that difficult to make, but it's really important. It's going to help us a lot. And here is why it is going to help us. What this means is that for a fixed n, the smallest Riemann sum is the left endpoint option. Why is this true? Well, if my function is increasing, here is my function. If I cut this thing up into pieces, the smallest options come from taking left-hand endpoints. That's the smallest each of these rectangles can get. Largest, can you see where the largest comes from? Take a moment and think about that. If this is an increasing function, what gives me the largest possible rectangle? It's the right-hand endpoints. If I take the right-hand endpoints, that gives me the biggest possible rectangles for the Riemann sums. So if you have an increasing function, that immediately simplifies things for you, because it means that you can say, well, the smallest Riemann sums are going to be the left endpoints and the largest are going to be the right endpoints. So let's just take a look at the limit of the right-hand endpoints and the left-hand endpoints, because if those come out to be the same thing, then using the Squeeze Theorem, we can say all of the other Riemann sums have to come out to the same thing as well. So we're going to look at the right and the left-hand endpoints, and then we're going to use the Squeeze Theorem. This is a nice little trick, and it works with decreasing functions too, because if they're decreasing, then the largest option comes from the left endpoints, and the smallest comes from the right endpoints, because you've got the same picture just happening in reverse. So if you have an increasing or a decreasing function, then that makes things particularly nice. And there's actually some additional properties here that you can sometimes break up the integral into different intervals, and on each interval it's increasing or decreasing. Now, I am going to work out the right endpoint case first. So keep in mind what we are doing here. We are doing the right endpoints for the integral from 0 to 1 of x squared. So fix an n. then delta x is going to be equal to 1 over n. Because, well, technically it's 1 minus 0 over n, which is just 1 over n. So I'm going to write it as 1 over n. And then my right endpoint Riemann sum is going to be the sum from I equals 1 up to n of I over n squared times 1 over n. I'm sorry, I don't know why that took me so long. The left endpoints are almost the same. The left endpoints are going to be the sum from I equals 1 up to n of I minus 1 over n squared times 1 over n. Now, you'll notice actually that the left endpoints, this is equal to the right endpoints minus n over n squared times 1 over n. So it's equal to the right endpoints minus 1 over n. Why is this important? The reason it's important is because notice that as n goes to infinity, 1 over n goes to 0. And so the limit of the left endpoints is going to be the same as the limit of the right endpoints, if the limit of the right endpoints exists. This is really important because it tells me that the limit of the smallest possible Riemann sums is going to be the same as the limit of the largest possible Riemann sums. So I said I was going to do the right endpoints first, but actually in the process of writing down these two formulas, we see that once we do the right-hand endpoints, that's all we actually need. We're done. Nobody needs to calculate, we don't have to calculate the left endpoints explicitly. Now, how do we do this? Okay, this is where things get complicated. More complicated. So, n doesn't change here. So this is actually 1 over n cubed times the sum from 1 up to n of I squared. Now, at this point, we need to use something called Fallhaber's formula. Although, technically, I think in this case, this is also known as the Nicomachus theorem. Because I think Nicomachus, I don't even know who found it. This is one of those cases where probably people worked out this formula in various times and instances, and who knows who was the first person to really discover it. I'm calling it Fallhaber's formula because Fallhaber is the guy for whom, actually, once again, he didn't really discover this. He came up with a generalization of this formula, but I think it might have been Bernoulli who came up with the general. Look, the point is, we're going to use a formula here, an identity that is not really obvious, okay? This sum is equal to the following formula. It is equal to n times n plus 1 times 2n plus 1 divided by 6. Once again, not obvious, but there you go. Now, there are similar formulas for other sums of powers, okay? So if you look up sums of powers, you will find all kinds of things. Actually, if you look up Fallhaber's formula, you'll see the general rule for doing this. But for the sum of I squareds, this is what you get. Now, what does this come out to be? So this is going to be 1 over n cubed times, when we simplify this, and I have this as notes, so I'm just going to write down what we get here. 2n cubed plus 3n squared plus n divided by 6. Now, keep in mind what we said about the left endpoints approaching the same thing as the right endpoint. By the way, we could do this in the same way. We could use the Fallhaber's formula again. The only difference is that this time we would be doing I minus 1 instead of I, and, well, really all that means is It's the same thing if we only count to n minus 1 instead of counting up to n. Otherwise, it doesn't change the formula. But we're not even going to have to do that because we see that the left endpoints have to approach the same thing as the right endpoints. Okay, so now, here is what we are going to do. We are going to make sure I didn't erase anything important. I did not. So this is going to be equal to 2n cubed plus 3n squared plus n divided by 6n cubed. Now, as n goes to infinity, this is going to approach 2 over 6, which is equal to 1/3. But remember, these are just the right-hand endpoint Riemann sums. So these Riemann sums approach 1/3. And these are the maximal Riemann sums. The minimal Riemann sums also approach 1/3 by the argument that I just erased. Therefore, what we can say is that the integral from 0 to 1 of x squared dx is going to be equal to 1/3. And another way of interpreting this, and this is kind of an interesting point, is that the area of this region, here's my y equals x squared curve, the area of this shaded region is 1/3. Okay, so we just went through proving this thing using Riemann sums. Now, it wasn't horrible. I mean, here's what's bad about it, really. It's thinking to use the Fallhaber's formula. Also coming up with Fallhaber's formula. But the problem is that in a more complicated scenario, we might have to use all kinds of other identities to try to find these limits. It may not be obvious at all what's going on. So this is why we want to get the fundamental theorem of calculus as fast as possible. Because the fundamental theorem is going to allow me to calculate these definite integrals by finding anti-derivatives instead of mucking around with actual Riemann sums here. Before we do that, though, we want to make sure that what we are doing is well defined. So here is the important theorem that we're going to prove from Riemann sums. If f is continuous on the interval from a up to b, then the integral from a up to b, f of x dx, exists. In other words, the limit of the Riemann sums exists, and the limit is independent of the choices involved. So how are we going to prove that this is true? By the way, it is really important that this is a closed interval. Closed interval is key. If this is not a closed interval, this no longer applies, okay? So be careful about that. Here is the way that we're going to prove this. What I want to do is for each n, or for some fixed n, let mi of n and capital Mi of n be the minimum of f and the maximum of f on the ith subinterval for the Riemann sum. In other words, you take the interval a to b and you cut it up into n pieces, and then on each one of those pieces, little mi is the minimal value of f, big Mi is the maximal value of f. These exist by the extreme value theorem, because this is a continuous function. So remember, the extreme value theorem says that on a closed interval, a function achieves its maximum and its minimum. And therefore, the maximum value and the minimal value do in fact exist. You can generalize this theorem slightly by getting rid of the assumptions of continuity and, well, actually, okay, no. What I should say is that there are cases where the functions are not continuous, but the Riemann sum still exists. And so I don't want you to think the Riemann integral only exists for continuous functions. No, there's plenty of examples where it exists and the function is not continuous. But proving it this way does require that we assume the function is continuous. And fortunately, for our purposes, we're usually going to be interested in continuous functions, or at least in functions that are continuous on, like, maybe they have some jumps in them, but you can break them up into pieces on which they are continuous. So these exist by the extreme value theorem. Now, the smallest Riemann sum is going to be the sum from I equals 1 up to n of mi of n. Why? Because the smallest possible Riemann sum comes from choosing my xi stars to minimize their value, or to minimize f. And similarly, the largest Riemann sum is going to be the sum from I equals 1 up to n of the maximal values of f, because I choose my xi stars to give me the largest possible value of f on that subinterval. That gives me the largest Riemann sum. Now, what I want to argue is that these converge and they are going, whoops, I forgot my delta x here. Now, there are a couple of things that I want to argue here. First of all, I want to argue that these sums are bounded. That's not how you spell sums. Why are they bounded? Well, they're bounded because f has a maximum capital M and a minimum little m on A up to B. And each one of these Riemann sums are going to be bounded between little m times b minus a and big M times b minus a. Why? Because, well, it's not too difficult to check. In fact, geometrically, it's sort of obvious. The point is that all of the little mi are going to be bigger than or equal to little m. All of the big mi are going to be less than or equal to the big M. So you break this thing up into small rectangles with different heights. They all fit inside the rectangle with a top at capital M, and they fit above the rectangle that has its edge at little m. So in other words, we have some function here going from A to B, and here is the maximum of the function, here is the minimum of the function. All of my Riemann sums are going to have to sit somewhere between the two rectangles, this big rectangle here and the small rectangle down here. Okay, I made a mess of the picture. I hope everybody can kind of see what is going on here with the picture. But yeah, so the Riemann sums are bounded between these two numbers. And they are going to, therefore, converge. Oh, how do we show? I'm a little, now that I say this, I want to be careful to say that these really do converge, because you could get something weird happening where they bounce around. Well, let's see why, assuming the limits exist, they are going to converge to the same thing. So the thing is that notice, as n approaches infinity, mi of little n and capital Mi of little n approach the same value. This is because f is continuous. So because f is continuous, if I take the interval to be smaller and smaller, for any given epsilon, there is a delta where f is within epsilon of its left-hand endpoint. But that means as long as my interval is smaller than that delta, I am within that epsilon. So that means the maximum and the minimum have to be within epsilon of f evaluated at the left-hand endpoint. And what this shows us is that all Riemann sums must converge to the same thing if they converge at all. So this is a really good thing. It tells us that for continuous functions, assuming the Riemann sums converge, got to converge to the same thing no matter what. Give me 1 second as I check through here something.